I would like to welcome my friend Meisam, Dr. Meisam Soleimani. He would be talking about biological growth with a focus on mathematical modeling and the finite element implementation. Meisam was born in Iran, where he did his bachelor and master's studies in mechanical engineering at Sharif and Tehran University. After that, he moved to Germany, where he had a doctoral scholarship from the Ministry of Science and Culture in Niedersachsen. He obtained his PhD from Leibniz University Hannover, working with Professor Peter Riegers at the Institute of Continuum Mechanics. Currently, he serves as a lecturer of finite element methods, as well as group leader in computation biomechanics division at the Institute of Continuum Mechanics. His field of expertise is in continuum mechanics and numerical simulation with application to biomechanics phenomena such as growth, arterial pathology, tumor modeling, and biofilms. I'm quite excited about what Meisam is going to be talking about. I'm looking forward to the talk. Thank you very much, Meisam, for accepting the invitation and joining us today. And I also thank all the participants who joined us today, and I'm looking forward to it. The stage is all yours, Meisam.
Yeah, thank you very much, Ajay. Do you hear me, right?
Yeah, I can hear you.
Okay, thank you very much, Ajay. Thank you for very kind introduction. I am also grateful that you basically invited me to this lecture series. It's a pleasure for me, no doubt about it. Okay, so as you also mentioned, the presentation is quite dynamic and interactive. So please, any of you who has a question, just open your mic and simply talk, and then we can discuss. Okay, as the title shows, the subject is biological growth with the focus on mathematical modeling and finite element implementation. First, a short introduction about ourselves. We are in Germany. Here you can see Germany, that in the German language it's called Deutschland. So it means that the land of Deutsch people, the land of German people. And here is a very nice view of the front of the university, the Leibniz University, with this beautiful horse statue here. It's quite an old building, I think, as far as I remember. I think it belongs to 15th century or 16th century, something like this. This is basically the house of Leibniz. That is, the university is associated with. This is a photo of 1800, around 1800, and this is the nowadays situation of this building. You see that it's pretty more or less the same. Then this is our group. Basically, this picture is an old group. You see that even Ajay, he is here. Yeah, we used to be in this IKM together, and we had such great days. Okay, so with this, I would like to just briefly talk about the outlines of my talk. First, I will give a very short introduction about the topic and just some applications of what we will be discussing. And then I would go to the theoretical framework with the focus on the isotropic growth. Then we will extend this theory into the anisotropic growth, and I will explain why this extension is required. It means that why this commonly used assumption of isotropy for the growth is not sufficient. So this is a very good question that we will try to answer it. Then I will talk about the FEM implementation, the important aspects that are to be taken into account in order to sort of translate that mathematical model into this numerical tool. And then I would present some examples with different applications, of course, biofilm growth. This is exactly what I did in my PhD. And then after that, I extend that model to tumor growth and bone ingrowth. I will explain these basically biological terms that are related to computational biomechanics. And then finally, recently we have been working on atherosclerosis. That means basically the occlusion in the arteries, so to say. I mean, roughly speaking, it means the occlusion in the arteries. That what we have developed using this growth framework is something that is quite new. because for this occlusion of the arteries, we have two, I would say, school of thoughts. The first one is basically the theory of deposition or sedimentation. That means that you have the calcification process within the arteries, and this is why that the arteries are blocked, right? This is like this old school of thinking. But a German surgeon who basically proposed a new paradigm for this process. So then we will explain how this growth process that at the end of the day is translated into the thickening of the artery wall may lead to this atherosclerosis. So we will discuss it also, and we recently published a paper on that. Okay, so what's the meaning of growth? What's the meaning of growth? Very simple. I mean, growth means that if you get a change of volume, or precisely speaking, in any increase in the volume, that particularly, of course, we are talking about biological tissues, because they are not inert. They are basically alive. So they have this capability to grow and get larger and get larger. And of course, it is due to the cellular activity. So here you can see a tumor, that the development of the tumor in the course of the time, you can see that how it can grow. The second example basically is the hydrogel swelling. Hydrogel swelling. Hydrogels, they are polymers that, simply speaking, if you just place them in the water, for example, they can absorb some water and start to swell. So from a mathematical point of view, the growth phenomenon and the swelling, they are pretty similar. Not the same, but pretty similar. So you can just at least establish similar mathematical framework for them. Another example is the brain growth. You see, this is the development, the natural development of the brain. You can see that the brain is basically confined within the skull space, within this internal, and so you see that it may come into the contact to the skull bones, and this is why that you can see the development of the wrinkles at the surface. Of course, if you want to interpret it more precisely, if you develop some wrinkles at the surface, so it means that you are trying to maximizing your surface that is associated with the number of the gray cells at the surface of the brain, while keeping more or less your volume constant. So the development of those wrinkles at the surface of the brain is related to this thing. So it's just to increase the surface, maximizing the surface while keeping the volume basically minimum. Another example is basically the biofilm growth. This is the biofilm growth. Just very shortly, what is the biofilm? Biofilm is nothing else than the aggregation of some microorganisms. If you look at this, basically, this material, it's composed of millions of bacteria that they have been glued together using a polymeric substance that is produced by themselves, and then the whole thing behaves like a solid, and then they start to reproduce, replicate, and you see that again they start to grow. So this is also the growth of the biofilms. That means these microorganisms is also pretty similar to all of these things that I explained. Besides growth phenomenon, we have something that is called remodeling. Remodeling, simply speaking, means that the density of the material increases. So what's the similarity between the growth and the remodeling? The similarity is that in both processes, we are talking about the addition of some mass to the system, right? If the tumor grows, if the hydrogel swells, if the brain grows, if the biofilms grows, so it means that some additional mass is introduced into the system. And basically this increase in the volume is a resultant of this mass addition. So this is the meaning of growth. But in case of remodeling, this mass, I would say, addition or injection or whatever you want to call, is not translated in the visible increase of the volume. Rather, it's translated into the local increase in density. So it means that here, instead of volume, the microstructure changes. So to say, the porosity changes. So by increasing the mass, by injecting some mass into the system, you get a denser microstructure. This is called remodeling. So from this point of view, growth and remodeling are different. So sometimes, roughly speaking, growth mostly happens in soft tissues. For example, tumor, brain, biofilms, any biological tissues or something like this. But the remodeling mostly happens in hard tissues like bones, nails, and this kind of things. I think with a very short introduction now, you have this flavor of this overall topic, what we are talking about. Okay, so just the last comments, I would say, disclosure to this introduction is that in both cases, either remodeling or growth, we are dealing with open systems. Open systems. It means that we have the transport, we have the transfer of the mass from and within the system. Of course, you can also talk about the reverse process. It means that if the volume of something decreases, so you would get this shrinkage, right? And in this case, instead of reproducing new cells, we are talking about the death or decay of the cells. So this is like the reverse process. The same thing for this remodeling also is quite imaginable. Okay, for the theoretical framework, what I am presenting right now is based on the two papers that we published. So for the more information, you might go to those two papers. The first one is 2019. It's based on this isotropic growth. It was published in Computational Mechanics. And then the extension to the anisotropic growth in 2020, sorry, it was published in JMPS. So it's a good idea. If you are interested, you might go and take a look at it. Okay, so the mathematical description of the growth starts with this very classical assumption of splitting the deformation gradient into some elastic and, let's say, inelastic parts. This idea has been borrowed from classical plasticity, precisely speaking, finite plasticity, in which you just sort of decompose your gradient, your deformation gradient, into an elastic and growth part. And this elastic is the part that is the free energy as a function of. That means that this elastic part is basically that part that is related to the energy being stored in the body. So this is why that here you can see the free energy as a function of right Cauchy-Green tensor that is basically constructed using this Fe, and then it's pretty like a hyperelastic, I would say, a free energy function. The point is this growth part. So this growth part, if you're talking about the isotropic growth, so we can assume that the structure of this tensor, it's an isotropic. So it means that you can capture it using the identity tensor and basically a scalar, right? So this isotropic growth at the end of the day is translated into a scalar, right? That is to be basically described, how this scalar, this alpha is evolved in the course of the time. And then you know from continuums mechanic that this growth tensor, if you compute the rate of this growth tensor, then you come up with this velocity gradient. This velocity gradient that is nothing else than the flow of, I would say, the flow of the material due to growth, right? Because as I told you, the growth is nothing else than the injection of some new mass into the system, and this new mass tends to find its space, so to say, and then this is why that you get this increase in the volume. So it's like blowing in the balloon, and then you're injecting some air into the balloon, and then this new air is trying to sort of open its space. This is why that you get this growth. It's pretty similar to that. And then,
sorry
yeah.
for interrupting. If I could ask a question,
Yeah.
so is there some kind of a thermodynamic, let's say, background on why we can do this elastic growth split? Just like the, I mean, is it just like taken directly from the elastoplastic, or is there some other thermodynamic considerations that are that can rationalize this decision?
Yeah, thank you, Ajay. It's a very good question, I think. I mean, this idea was borrowed in 1994 by Rodriguez, and then after that, it was followed by Tauber's and other. I think it has simply been borrowed from plasticity. That you know that in plasticity, it was basically invented or introduced by Lee, right? It's quite an
Right.
old thing. Yes, it's quite an old thing. I think it's this idea has been borrowed from them. But I will talk about the thermodynamical consistency, the concerns that people always raise. And you are right. I will talk about it. I will
Sure.
talk about
Okay.
it. That what are the importance? For example, as you know, that in plasticity, for example, at the kinematic level, we assume something, but then we show that the dissipation associated with this thing is positive. That means that it doesn't violate the second law of thermodynamics. Yeah, but here we need to take into account some more considerations that I will talk about. But I think it was a very good question. Yeah. So we were talking about this, the rate of this Fg. This Fe, as I told you, is related to the elastic response of the body. It's like the solid body, like this normal solid bodies, and this growth part is related to this biology. And then this growth part, you know that this tensor, the product of this tensor, if you compute a trace of this thing, you would get the divergence of the velocity gradient associated with this rate. And then that 3 comes out due to this identity tensor. So this is the reason. And then, so at the end of the day, the rate of this growth part is nothing else than the rate of this alpha, right? It's quite intuitive. And then the last chain is just to connect this evolution in alpha into the biology. So here we need a new field. So in addition to displacement, that is the mechanical, I would say, indicator of the mechanical problem, we need a new field. And that field is the concentration of nutrient, for example. Keep in mind that all growth processes, they are related to the concentration of a second agent or a second substance, because as I told you, the growth originates from the cell division, and those cell divisions, they need some nutrients, so they consume some new masses. As I told you, I mean, the growth is directly related to the addition of new mass into the system. So we have not only the displacement, but also we have the concentration of something. And that concentration of something is basically governed by this very simple diffusion equation. You see that this is basically the weak form of the Laplacian operator, right? This is the d del squared of c or something. That in the weak form, you can basically construct this one. And then these are the fluxes at the boundaries. So it's nothing else than the diffusion equation, right? Simply speaking. And then the coupling between these two equations is established exactly here. So we directly relate this evolution in this alpha, that is to capture this growth, to this concentration using this very simple linear equation, right? You might ask me that why this relation? I would say this is the simplest in the world. I mean, it's a very linear dependency, and then the more concentration, the more growth. For sure, this K1 and K2, they are material parameters that are to be determined using the experimental observation. And then depending on this positiveness or negativeness of this K, you might talk about even the shrinkage. For example, if K is very large, you can see that you are getting some negative divergence. That means that you are creating some sink into the system, and then you would end up with the shrinkage instead of growth, right? This is like a mathematical model that we proposed. So you might think of other, I would say, kinetics as if you've seen for some other biological systems, we have different basically relations here. Okay, as I told you, so from a mathematical point of view, we are dealing with two primary variables, two field variables, the concentration and then the mechanics, the conservation of the linear momentum. That here you can see the weak form of the basically equilibrium, the balance of momentum that has been described in the initial configuration. Just be careful about a very important thing, that this equilibrium, originally you need to write it in the current configuration, but here we've written it in the initial configuration for the mechanical balance. It's a very, very tricky but extremely important things. And then here is the structure of the free energy, as I explained to you. That's this J basically is a determinant of elastic part of the deformation gradient, and this C, it's a pretty standard procedure in definition of the free energy. And the second pillar, Kirchhoff stress, can be extracted using this free energy, right? This is the basic assumption of hyperelasticity. That means that the stress can be extracted from a free energy. And that is what we are doing, using this pullback and push forward, using this push forward operators from the left and right. And these are pretty standard things that I don't want to spend the time more on that. Okay, with this, I would like to show some preliminary results about it, and then we will talk about the extension of this model into anisotropy and why. So right now, yes, go ahead.
On this slide, this free energy, is this per unit reference volume? Is it per unit volume, or is it just free energy?
Yeah, it's free energy. This psi, you mean, right?
Yes.
Yes, this psi basically is the Helmholtz free energy. This Helmholtz free energy, that is basically, I mean, if we were talking about the Hooke's law, then Helmholtz free energy, it's something similar to the potential energy in a spring. So 1/2 kx squared, roughly speaking. But here, if you are in the hyperelastic framework, then your free energy is a function of the invariance of C, and that C is related to this elastic part of this deformation gradient. So the trace and the determinant, and of course the cofactor that here is absent, but this is the overall concept of that. If you are in the framework of hyperelasticity, then you can postulate existence of a free energy that is a function of the invariance of that basically deformation gradient. So this is the way that it is defined. And you see that it has two parts. This part is a function of this basically the determinant, and this part is a function of trace. So this is more or less is going to capture this volumetric part. This is going to capture this isochoric part. So this is also this interpretation of that split, that's additive split in the free energy, right? Yeah. Of course, you have multiple choices for that. It's not the only free energy function in the world. I mean, you have tens of them, different, so Hookean, like Money-Rivlin type, Ogden type, and so on and so forth, and different definition for that.
Yeah, generally we take free energy as per unit mass or per unit volume. So is this just the absolute form, or?
Yeah, it's a very good question. It's a very good question. So you see that depending on how you choose these parameters, let me just restate your question for the audience, because it's a very good question. The question is, for the open systems, is it a good idea to define the free energy in terms of energy per unit mass or energy per unit volume? This is the question. So you know that all strains, they are dimensionless. So this guy doesn't have any dimension. These are dimensionless. So the dimension of the free energy comes from the dimension of the parameters existing in the free energy. So you know that these parameters, roughly speaking, let's go back to the principles. They are like Hooke's law, Hooke's law, and this Young modulus, let's say. And the Young modulus, you know that it's like Pascal or megapascal, and Pascal is Newton per square meter, right? Newton per square meter. If you multiply the denominator and the numerator into meter, then you are talking about the joule per cubic meter. Joule per cubic meter. So this free energy is basically the free energy density, more precisely speaking. That means that it's the energy per unit volume. Energy per unit volume. And also the stress is like this. The stress is also something like energy per unit volume, because Newton per length squared is equivalent to energy per volume. Because you know that the strain is dimensionless, right? The strain is always dimensionless. But as you mentioned, there is two basically possibilities. If we are talking about the growth phenomena. If we can define the free energy per unit mass or per unit volume. For sure, if you want, you can convert them together by just dividing by rho, right? Because if something is per unit volume, then if you just multiply it by rho, that is meter cubic divided by kilogram, then you can convert this thing into the basically joule per mass, joule per kilogram or something. But the problem is that if you define like this, then you need to also treat density, rho. You need to also treat density as a variable. Because as I told you, the key thing in the growth and the remodeling process is that either density or the volume changes. For the growth, basically the preservation of density is something that is justifiable, because you can say that this new mass creates more volume at the cost of keeping density constant. But here, the new mass doesn't create new volume. Rather, it increases the density. So this is the only consideration that you need to be careful about. Is it clear?
Okay, thank you.
Yeah. Okay, let's go. Let's start with the first and simple example. It's a slab of a material. You can see that basically it's a cube basically. So we apply the zero concentration here, zero concentration at the bottom, and the maximum concentration at the top. You can see that it starts to swell using that model. And over the time, you can see that since it's a 1D problem, everything is linear. What we expect to get is a linear, basically, profile for the increase of this dimension that is h. So with respect to the time. So it was the first example that we tried to solve in order to calibrate our model to see that if it works properly. You can see that this is the distribution of that basically nutrient that I was talking about. And here you can see that why I basically stressed that you need to solve that diffusion equation in the current configuration, because you need to get this uniform sort of distribution for the concentration. If you extend this problem into a I would say, rectangular geometry, it's basically a spherical, precisely speaking, semi-spherical geometry. You see at the bottom, you apply the zero concentration and you apply the maximum concentration at the exterior surface here at this curved surface. You can see this is the boundary condition, and of course it's free. So in this case, we are talking about free growth, which means that the body can freely just simply grow, right? Without any obstacles, without any constraint from the external. I just want to make you prepared for the necessity of anisotropic growth in case of unconstrained growth that I will be talking about in a minute. Here also you can see that this is the distribution of that nutrient. So here this is zero, the maximum is the exterior surface. I mean, an application of that is if you just submerge this guy, for example, into a solution, and then of course the exterior surface is exposed to the most basically nutrient. So this is why that you can see the nutrient is the maximum here, and then you get this contours across the bulk of the body, and then you have this zero things at the bottom. But nevertheless, you can see that after 200 hours, you see that it swells, it grows, and everything is isotropic. So the sphere remains sphere, right? The sphere remains sphere. It gets basically larger, and these are the material properties. For more details, you might go to those two papers that I was talking about. Then I want to talk about anisotropic growth, why this anisotropy is important. As I explained to you at the very beginning, you see that in the development of the brain, as I told you, we have this formation of these wrinkles or foldings at the surface of the basically brain. I mean, from a mechanical point of view, Professor Kuhl is working on this stuff in Stanford. They are very experienced in this modeling, and she is basically one of the pioneers in the field. I mean, I'm pretty sure that if you are a mechanical engineer, you can guess what happens. What's the reason of this this morphology, this particular morphology at the surface? I mean, the reason is that we are talking about the growth of a material that is constrained, that is limited to a space, right? Due to this very stiff skull bone. And then what happens? So if it starts to grow, then you would develop some compressive, I would say, stresses or load, and then these compressive things may lead to this local buckling, right? This local buckling. Those basically wrinkles are nothing else than the appearance of those buckling modes, those local buckling modes, and this is why. This is the, I would say, the interpretation of these folding from a morphological point of view, from a mechanical point of view. Of course, you might ask yourselves that, so what is the role of genetics here? So what's the role of genetics? The question is that if these gray matters tends to fold due to this mechanical driver, or is there any genetic behind that? So it tends to basically reshape itself rather than basically a mechanical response to that. Of course, here there is a debate, and two, I would say, school of thoughts. They have some advocates, and everybody is trying to just explain it. But it's a commonly, I would say, commonly acceptable paradigm in this regard. It means that one can explain the formation of these wrinkles at the surface of the brain in this mechanical framework. Another example of this constraint growth, that means that by constraint growth, I mean the growth that is limited, or it's under some constraint. It's under some constraints. Another example is this bioreactors. You see that these bioreactors, they are used for the purification, for the water treatment, for example. And then if you look at those units there, you see some sort of skeleton, and then they are basically colonized by some microorganisms that, as I told you, they are called biofilms. And then those biofilms, if they want to grow, then they are confined, because just like a defined space there. So there's a window beyond which you cannot basically take space. And then this is also another example of this growth, constraint growth, and that's pretty similar to that. So in these two cases, we are talking about that. And if we want to present a mechanical model of it, we can think about like this little cube, that you have some barriers in it, and then you have this little sphere there that is expected to grow, but it should respect those mechanical rigid constraints. That means that here a contact from a mechanical point of view, it's a part of the story. So in order to clarify and in order to shed more lights on that, I would like to show simple examples. I would say that always one need to look at the simple example. You see that this is this cube, it grows. You can assume that it's basically the first example that I presented. But the point is that it's confined, so you have some walls. This is basically 1/4 of the model for the symmetricity. So you can see that it's a growing cube within a shell cube, right? And then so it can grow to the moment that basically it touches these walls. But the important thing is that if you look at the growth, you see that this is time and this is the volume, right? The best indicator of the growth is the volume. You see that the volume increases, and after that it remains constant. It's quite intuitive, right? It's nothing special. But if you look at the stresses, you can see that you have three kinks in the stresses. They are principal stresses, basically, in X, Y, and Z direction. You have three kinks corresponding to three consecutive contacts. You see this is the first contact, and the second contact, and finally the last contact. You see that after the last contact is established, we have a drastic change in the stresses, because the material is completely confined, and then but still that FG start to basically evolves. Of course, in these two cases, we have assumed that those walls are permeable. What does it mean? It means that the access of the body into the nutrient is not hampered by those walls. So those walls, they are only mechanical walls. You can assume that they are, for example, perforated. So we have the basically provision of nutrient to the system. So those concentration of the nutrient exist. So the body receives some nutrient and it tends to grow, but it cannot due to this mechanical obstacles or rigid walls. So this is the concept behind that. So this is the question, that how should we treat in these two cases if we have a confined growth? You see that in this case, one should get a feedback from stress. What does it mean? It means that if the contact is established, then you are experiencing increase in the stress. And if you can define your growth to be dependent on the stress, then maybe there is a hope for just remedy this problem. Because right now, as I explained to you, the growth is only a function of concentration, right? I just want to go back here. You see that the growth, this FG, is only sensitive to concentration. So as long as you have the concentration or the nutrient, so it starts to grow, and it doesn't care about the mechanical stress. So it's indifferent. It's indifferent to the increase in the mechanical stress. So this is the idea of anisotropic growth. And from a biological point of view, it's also justifiable, because as I told you, the growth, if you look at the growth at the cellular level, so we are talking about this binary divisions of the cells. So this is like the parent cell, the mother cell, or whatever, and then it wants to split. So this basically this division of the cell into the two, and then you would get this one. And then the question is it possible for this parent cell to just give birth to these two little daughters in any cases? The question is no. I mean, if the material is under extreme compressive loads, so it cannot happen. So this is why that even from a cellular level, the growth should be a function of stress. So it should be also a function of stress. I mean, in this case, the driving of the growth is the nutrient, right? It's pretty intuitive. But the point is that it's not only about driving the growth, rather it's talking about steering the growth. That means that this power of the growth comes from the nutrient, but how to guide the growth and how to control the growth or how to stop the growth should be influenced by the stress. You see that in case of isotropic growth, if we talk very simple, a cube remains cube because all the parts of the body tends to grow isotropically. So it's like this. But if you're talking about anisotropic growth, the idea is that if you start with a cube, so the cube doesn't necessarily remain cube. So there is some preferred direction. So for example, if you want to just create, let's say, 1 cubic meter of new volume, right? This 1 cubic meter of the new volume in case of isotropic growth is distributed isotropically. So everything is symmetric. But in case of anisotropic growth, if you start with this, then you might end up with this. Keep in mind that the volume of these two guys are the same. So it's about how to distribute the newly generated volume or newly generated mass, precisely speaking. You might have also different options, alternatives like this. In this case, the preference direction is this. Or you might have like other directions, something like this. So this is the idea how to formulate the anisotropic growth. And to do that, that means that to bring a directionality to growth function, to FG, to this growth tensor. So I was inspired by finite plasticity again. I really like this finite plasticity. I think it's really the foundation of everything. So if you are familiar with finite plasticity, you know that in finite plasticity, when you define your evolution equation, so in the definition of the evolution equation, you have two things. The first one is the magnitude of the evolution equation that is captured using this lambda plastic multiplier, and then the direction of plastic, basically a plastic strain, so to say. And it comes from the yield function. So there exists a yield function. You take the derivative with respect to tensor, sigma, that is a tensor, so it gives you a tensor. So it's a tensor, it's a scalar. So the direction of the plastic strain is dictated by this guy, but the magnitude is dictated by this guy. And you know that in this case, it's called associative plasticity. So there exists a yield function, and you know that this guy is perpendicular to the isosurfaces of phi. So this is the idea behind that. But here we do more or less the same thing. The idea is that I want to explain it very simple so that you can understand it. So the question is how to create this link between the growth and the stress. So this is the question. You know that in plasticity, this link exists because in plasticity, if the stress reaches a certain value that we call yield stress, apart from the existence of hardening or not. So basically this dependency has already been established. Here what we do is just to compute eigenvectors of the stress. So N1, N2, and N3 are the eigenvectors of the stress. And then we sort of distribute the growth. You see that this alpha dot over 1 plus alpha dot is exactly the same thing that we obtain for the isotropic growth, right? It's like this scalar that was supposed to capture this isotropic growth. And then you see that just for one moment, imagine that this doesn't exist. So we have delta 1 over delta, delta 2 over delta, and delta 3 over delta. And delta is nothing else than the summation of those three deltas. So what we do is that we just do the spectral decomposition of the stress at any point. We find the eigenvectors, we find the eigenvalues, and depending on the magnitude of the eigenvalues, delta 1, delta 2, and delta 3, we just build this growth, I would say, rate, this L, that is the velocity gradient associated with this growth FG. You know, this L basically is the velocity gradient associated with that FG that has been basically pushed forward to the current configuration using this FE. And this is the way that we built it. So the more tensile load you have, the more growth you get. And then we can also incorporate the condition of growth cessation. That means that the more stress you get, the more positive stress, let's say. The more growth you get, so it means that you are basically making a preference. You are incorporating a preferred direction. So that guy tends to grow in the direction with the I would say, largest tensile stresses. So, and if something is compressive, then the growth in that direction is smaller. Until we get a critical value that is a material parameter, you can define it. And if the stress in that direction exceeds this value, then you would simply stop the growth. So this is the way that you basically incorporate this anisotropic growth relation. You see that first of all is anisotropic. Why? Because you see that you have three basis vector. If all of these delta 1, delta 2, and delta 3, they are the same, then you can just factorize these delta, and then the summation of those and 1 and 2 and 3 dyadics gives you the identity tensor. So you restore that isotropic growth. So with this way, we are, simply speaking, we are basically manipulating the identity tensor in a way that we have some preferred directions. This is the first point. The second point is that we have this cessation condition, this cessation of growth. That means that if the compressive stress reaches a certain value, then the growth stops. The growth stops. As I told you, that those things, they are the eigenvalues and the eigenvectors of basically Cauchy stress. So this is the idea of that. And then, of course, for the implementation, pretty similar to plasticity, finite plasticity, you need to use this exponential mapping in order to integrate this guy. Because don't forget that if you are talking about the evolution equation, we are talking about the rate of something, rate. And that rate has to be integrated. Is to be integrated in order to sort of recover that FG. That is the thing that we were looking for from the beginning, right? I mean, we started with the split of F into FG and FE. And then this is the well-known exponential mapping that is used in plasticity, in finite plasticity, that you are familiar with that. But keep in mind that if you want to implement it, the if conditions are the bloodiest creature in the world. If you want to use implicit computational mechanics, and you already have this if, I mean, just look how complicated this implementation is. First, you need to compute the eigenvalues and eigenvectors of the stress at any point. So imagine that you are at a particular Gauss point. You need to first look at the stress tensor, compute its eigenvalues, eigenvectors, and then build your growth, and then apply this if. Apply this if. And that if, of course, you need to regularize it. So this is just a little thing for those who are interested in this little things in implementation. So you need to regularize this point. Otherwise, you would get a very bad tangent of it. Okay, the last thing that I want to talk about is another feature that may be brought into the picture. And the idea is to use something similar to thermal contact. You know that the mechanical contact is a classical problem, right? It's a classical problem. You have two bodies, they come into contact, and then that's it. Some stresses, you have the contact pressure is developed here, and that's it. You have the gap function, everything. The framework of thermal contact can be used also here. It means that imagine that in your mechanical contact, you have not also this mechanical deformation, but also this thermal effect. That means that the heat should transfer across this contact zone. In that case, what you can do is that it exists in the literature. I mean, maybe some of you are familiar with that. The key idea of developing this thermal contact formulation is that this conductivity, or let's say this heat flux that is defined across this contact area, is defined as a function of pressure. So the more pressure you apply between these two bodies, those asperities come into contact in a better situation. So they are just fit into each other sometimes. And then, so the more pressure you have, the more transfer of the heat here exists. Of course, you might think of just filling those space with some third material that, I mean, in this case, you need to talk about the three media contact. So and it's not the case for what we are discussing. So we are talking about two bodies that's come into contact. The more pressure you have, the more flux of the heat you have. So this is the idea that we used for the developing a I would say a multiphysics contact, in the sense that if we have a contact between a growing body and the wall, depending on the pressure developed between the growing body and the wall, we can sort of adjust, or let's say manipulate the flux of nutrient, right? This is the idea. So we use this analogy in order to create this multiphysics contact. So a contact in which the transport of the nutrient is also involved, so to say. So this is the idea. Okay, for the implementation, it's believe me, it's 90% similar to what we do in plasticity. That means that for the growth part, we assume that whenever I'm saying growth part, you can directly replace this word with plastic part. So you assume that the growth part is equal to the previously converged one, and then you compute the elastic deformation with the assumption of previously plastic part. And then after that, you can compute your right Cauchy-Green tensor. From the free energy, you can extract your stress. And then, of course, if you want to convert, it needs to be converted into the Cauchy stress, because you remember that our growth, that was a spatial quantity in the current configuration, is to be defined using the Cauchy stress, not the second Polakoff stress. So, and then after that, we compute the eigenvalues of sigma. Then we apply that condition of growth cessation. That means that if the sigma exceeds this value, it's prescribed to 0. And then we can build our anisotropic growth function using what I explained to you. You see, this is the eigenvectors of sigma. These are the eigenvalues of sigma, sigma 1, sigma 2, and sigma 3. And this is the summation in the denominator, and this is alpha dot over 1 plus alpha. That is exactly what we had in the isotropic growth. So it's basically a new rate for the growth that is anisotropic instead of, and this anisotropy has been created by us by just extending intentionally this isotropic, this identity tensor in some direction. So these are not equal. We have some preferred direction in the growth. And then we have a local equation. That local equation comes from that evolution law. You remember that that growth was a function of concentration. So this is to be enforced locally. And then we have the integration of the growth function, that is this exponential mapping that I explained to you. And then, of course, this local problem creates some local tangents that are to be utilized in the computation of the global tangent. That's it. And the global tangent is computed. That's nothing else than the derivative of the residual associated with these weak forms. You see that it's like the pseudo potential by just summing up these two terms together. So this is the mechanical part, and this is basically this Laplacian operator for that governs the diffusion equation. And then you compute your global tangent, and everything is embedded in a Newton-Raphson equation that finally you can iterate and solve it. You see that for the elements, you can use the normal elements. For example, if we are in 3D, we can talk about 8 nodes element, like this brick, right? Everybody is familiar with. And then at each node, you have 3 displacement, of course, and 1 concentration. That basically it's a scalar that reflects the availability of the nutrient. So it's similar to temperature, so to say. And then, of course, this coupling between these two was already explained here, right? It's the way that they are coupled together. This is the point. And of course, at the Gauss point, we have some basically historic variables that are called alpha. I told you this alpha. This alpha is exactly similar to this plastic multiplier that is defined at the Gauss points. And then this local problem is to be solved at the Gauss points. So this is the way that we implement it. We use this AceGen. AceGen basically is a library in Mathematica. So that means that you can define these things, and then it gives you the basically, I mean, you can choose either C code or Fortran code or whatever you want. So it used this so-called automatic differentiation in order to convert these symbolically defined, I would say, equation, and then export this subroutine in Fortran or C, and it can be used in whatever solver that you have. For example, we use the user element, the ANSYS. So we created our user element here in AceGen, and then we create a user element in Fortran. I mean, for those of you who are familiar with ANSYS, you know that in the ANSYS, if you want to define a user element, it should be a Fortran file, and then it should be compiled, and then you need to basically use that user element. It means that a particular element that you have created. So, and then using this stress-dependent growth, you see that if we do it, then we see this nice nice evolution of the growth. You see that once it comes into the contact, then the growth stops here in this direction. But you see then here stops. Here is the region that grows very fastly. Even you can see if you look carefully, you can see that, I just want to stop the movie here. You see that here it's like a concave, it's not a straight, because this region, the growth has stopped, this region also has stopped, so the top surface is not a flat one, right? The regions close to the walls, they grow basically slower, more slowly compared to this region, for example, that still has no constraint, right? It's completely free to just simply grow. And if you look at the evolution of the stress, you can see that you don't have those sharp kinks, right? Here again, you have three basically contacts, and then the point is that at the end the stress remains bounded. It's very, very important. You see that in plasticity, the outcome of plasticity is that basically it crop your stress. That means that your stress remains bounded. This is very important. For example, if you are talking about the crack propagation, at the tip of the crack, you know that from a mathematical point of view, the stress goes to infinity. But if you introduce plasticity, then plasticity basically makes your stress evolution to be bounded. So this is very important. So this stress dependency embedded in the growth at the end of the day is translated into this very nice evolution of the stress. This is stress 1, stress 2, and stress 3 in X, Y, and Z direction. You have three events of contacts that basically they happen one after each other. The next example is it's an example that mimics that bioreactor that I showed to you at the very beginning. So we have a growing sphere in the middle, and then it's confined in a cube, and then you have some rigid bars. So it's like it's a very complex geometry, available complex geometry that is to be filled. So if this sphere wants to grow, it's not free to just grow. So it has some barriers within this cube. And if you do that, you can see that this is the way that it grows. You see that it's super flexible. It's super flexible. So it's almost like a fluid. It's almost like a fluid. So basically it finds its way in the available complex geometry that we have. And here basically is the stress. You can see that the regions with the stress, the regions with the contact, you have a high stress, and this is basically the concentration. You see, this is the concentration. At the very beginning, the whole sphere is exposed to this concentration. I mean, this exposure to the concentration, if you want to look at it from experimental point of view, you can assume that this cube is filled with a solution, with a water or with a fluid, and that in that fluid we have that concentration, and that this growing sphere is exposed to that concentration. Of course, if it grows, this water should go out, right? We have assumed that, for example, we have some holes here, so the walls are permeable. So if this growing sphere increases its volume, so in order to accommodate this newly generated volume, so you need to sort of remove some of the fluids. So some of the fluids basically can be drained, or it drains using this permeable wall. This is what you can imagine, of course. This is what you can imagine about the real physics of that. You can see that if the contact is established, also the provision of the concentration also is restricted. So surfaces of the body that are not in contact, they tend to grow faster. Okay, the next example is the both ingrowth process. Just shortly explain what is the ingrowth process. Ingrowth process means the integration of the bone in the vicinity of the implant, of an implant. If you look at the surface of the implant, it's not flat. So at the due to roughness, you have some topographical features at the surface of the implant. So you see this little hills and basically valleys. And then the point is that if you look at it from a closer look, you see that this is the implant and this is the surrounding bone, right? And then if we say that the implant is fixed in its place, it means that the bone has grown, and then you have this perfect integrity between the implant and the bone. So this is called the bone ingrowth. Bone ingrowth means I would say, I mean, there is a terminology for that. It's called osso integration. Osso means bone, right? So the integration of the bone into the implant is called osso integration or bone ingrowth. This is also, if you look at it from this perspective, this is also a confined growth case. That means that you have something that starts to grow and it should basically fills those available spaces. So you have a very, very complex geometry that this growing body is to just fill that. And this mechanical interlock between these two is established. So there's one of the failure modes of the implants is called loosening or aseptic loosening. That means that the implant is not fixed in its place. So after, for example, after a few weeks, so the implant is not stabilized, I would say. So that means that this process has not been established properly. So you don't have this good connection between the implant and the bones. So this is the bone that basically starts to grow. Keep in mind that here, compared to what I said in the first or second slide, if you're talking about the bone growth, so it's remodeling. So we should not see this basically visible increase of the volume of the bone. The point is that here we are looking at the microstructure. That means that even the bone ingrowth, if you zoom at the level of this asperities, at the level of this microtexture of the roughness of the implant surface, then there you can see that grow, and that so it exists there at that scale. But if you look at this scale, that means I would say the macro scale, of course, yes, you don't see it. So in this scale, if you want to remodel this bone ingrowth, you need to use this remodeling framework, that you just see the increase of the density. But if you zoom and go to this micro scale, I would say, or at least the length scale of this surface roughness, then in this case, what you see is exactly like this. So because this is nothing else than the growth of these osteoblasts. That means the cells that basically contributes to the growth of the bone. So this is also another example of confined growth. You see this super flexibility in order to just fill this available space, this very complex available space between those valleys and hills is not possible unless you have a very good definition of the growth function that is to be isotropic and is to be stress dependent. That means that if the growing body faces some rigid wall, so it should have the flexibility to find its way in another directions that is still free. So this sort of smartness or flexibility is basically conferred to this growth model if you use what we explained to be the isotropic growth. And if you look at this, the integrity of this bone and this implant surface, I mean, I have used a transparent representation for the implant so that we can see it. So you see that exactly, you can assume that you can assume that it's a very soft material and it's a very rigid material, and then you have this imprint. So it's exactly like imprint. So those hills exactly feel the valleys at the surface of the implant, and then if those hills come into contact, they create a valley in the bone. So this is why that this mechanical interlocking has been completely established between this, and then this is the basically the bone ingrowth. The next example is the tumor growth. You know, it speaks for itself. Tumor means that you have basically a, let's say the spherical, I would say, lesion, and then it starts to grow. And this is the brain. These are the geometrical things. And then we have assumed that the growth of the tumor, we have assumed, it's only an assumption. They assume that the growth of the tumor is only controlled by the availability of a blood vessel. So it means that, you know, that in the brain we have a lot of vessels. We have assumed that we have only one vessel. It's only an example. And then depending on the proximity of the tumor to this source of nutrient, then it tends to grow. It tends to grow because, as I told you, the tumor is nothing else than, the tumor is, the cells of the tumor are pretty similar to the cells of the brain itself. Healthy, I would say, tissue. So this is unhealthy due to overgrowth. So in this model, we have used this growth model for this guy, and the without growth model, I would say, for the rest of the brain. So the brain doesn't grow. But the point is that if the tumor grows, you see that this is the tumor that has grown. And this is basically a cut of the model, and this is the source of the nutrient. You see that it tends to get larger and larger and get closer to the sky. And here I have compared two cases, isotropic growth and anisotropic growth. In case of isotropic growth, if you use the isotropic growth, you get like this, and then there's no stop for the tumor growth, because there's no stress feedback, right? And in this case, basically the brain explodes because there's no barrier to that. But if you incorporate the stress effect, then in this case, the growth is restricted. So it means that the tumor grows, and after a while, it reaches a stable size. And it has also been observed from an experimental point of view. We have some tumor that are called dormant tumor. They are like a dormant, basically volcanoes. So they are there. They don't get larger anymore. So it's sort of an equilibrium has been obtained. And these sort of tumors, they are not malignant. Most of them, they are benign. So this also has been observed. But of course, it's only just one interpretation of this phenomenon. You can see that how these things start to grow, and even the shape of the tumor, if you use the anisotropic growth, you see that this is the ratio of the volume. This is the initial volume. Keep in mind that we always start with already existing initial volume, because this growth doesn't talk about the initial tumor development. So you need to keep it in mind. It's something that has its root in genetics, or at the cellular level. We assume that we have like a little tumor, and then we let it grow. So this is the very important things. Again, these examples, they were published in this JMPS. So for those who are interested, you may look. The last example is this atherosclerosis process, that it's quite a new thing. As I told you, you know that this is the artery. The structure of the artery is multi-layers. So you have the inner layers, and then the intermediate layers and the outer layers. The adventitia, technically speaking, media and intima. And then the point is that there are two schools of thought for this stenosis of the artery. That means the occlusion, or getting a narrowed, I would say, section in the artery. The first one is the calcification hypothesis. That means that due to some fatty materials, LDL, cholesterol, or whatever, we start to build up some sediments, some depositions within the inner layer of the artery, and then basically the cross section of the lumen, that is called this void section of the artery, decreases. So this is one way of thinking. But this process is called atherosclerosis. So atherosclerosis means the appearance of stenosis within the artery, And then Axel Havrich, who is a surgeon in Germany, he proposed a new idea. He proposed a new idea about the this pathology, this atherosclerosis. And what he said is that this formation of this basically bulge within the cell is due to this reason that I explained. So you see that if the artery is very thick, the artery itself needs some capillary in order to provide the artery with the nutrient. Because keep in mind that the artery itself is a living thing, so it needs nutrient. So the inner part, they are supplemented by the diffusion mechanisms, because this internal part is filled with blood, right? The red blood cells and the blood. So it can diffuses, and it's sufficient to basically nourish those cells there. But for the exterior parts, you have some capillaries that basically provide the wall arteries with the nutrient. And the point is that it's a very new paper that we published. It was in special issues on COVID-19. And what's the relation between this thing and COVID-19? The relation is that if these capillaries are blocked due to fine particles, for example, in cities with air pollution, with aerosols, with so-called 2.5 micron particles, or viruses or bacteria, then if they are blocked, then you have inflammation here, because this exterior parts of the wall doesn't basically receive the required nutrients, and you get some inflammation here, and finally you get an overgrowth. And then so this stenosis is due to overgrowth of the wall, not due to the deposition of the fatty materials. This is the new hypothesis that I was talking about in a very simple language. So instead of out-in theory, he proposed an in-out theory. That means that this thickening of the wall happens not due to sedimentation, rather due to this overgrowth or inflammation within the media. So this is, in a very simple language, the explanation of that thing. Of course, I mean, in practice, what we have is that once this, this initial atherosclerosis is developed, we might have both mechanisms. That means that if you already developed some overgrowth within the inner layer of the wall, then of course it is susceptible to the accumulation of fatty materials and basically calcification process. But this is the question is how it's triggered. You see that here this inflammation start to develop. You see, this is the fine particles, the bacteria. It's not a simulation, keep in mind. It's only an animation. It's only an animation just to make you aware of the problem. And what we did for our hypothesis of overgrowth, so now you understand that what's the relation of atherosclerosis and the overgrowth. Atherosclerosis is perceived as an overgrowth process within the wall of the artery. And we use this very simple model. It's a 2D representation of that. Again, we introduced like this initial inflammation. We coupled our model, our growth model, using with phase field, that I don't know if you are familiar with that or not. I mean, it's a talk for itself. So we coupled that thing with this phase field modeling. Phase field modeling is, you can think of a a Boolean thing. So if it's red, it means 1. If it's 0, it's blue. So, and then if something is red, it means that you have inflammation there, otherwise you don't have. And then depending on this inflammation, you get this overgrowth that at the end of the day leads to this stenosis within the wall. Stenosis within the wall, and these are the results that you can see here. This is the basically that inflammation region, and this is the region that has been deprived from the nutrient. You see that very complex morphology can be captured using this phase field combined with this growth model that we had. Okay, so with this I would come to conclusion and the outlook of the work. So you notice that a new theoretical framework analogous to finite plasticity was developed for the growth. The FEM implementation in the context of a multiphysics user element for ANSYS was presented, and the application of this problem was basically demonstrated in different biological tissues like tumors, arteries, microorganisms, or biofilms, and so on and so forth. The only thing that remains is the considerations about thermodynamical consistency that Ajay truly raised a question about. I mean, for example, in plasticity, everything has been well established. We know that in plasticity, it's taken from this maximum dissipation theory. So it means that the evolution of a plastic deformation is defined in such a way that this dissipation is maximized, right? It's already there, it's built in. But if you remember, here we didn't talk about the second law of thermodynamics. We didn't talk. So we assume that everything works good, and we define the evolution of the basically the growth function heuristically. That means that we said that, okay, we just create a stress dependency here, and then depending on the extent of compressiveness of the stress, we basically bring some directionality or preferred direction into the growth. That's it. But we never checked if this is thermodynamically consistent or not. Why this is complicated? The reason is that it's open system. So if we need to sort of extend already existing continuums mechanic relations into the open system, so that we need to account for those things. So we have some sources of entropies due to this openness of the system, and sources of basically mass, and for sure sources of momentum and others. So this is the reason that it's complicated. And it's I mean, some authors, Alan Gourley, for example, in UK, he has written a book on that, on this growth phenomena. It's a very good book. I would recommend reading it to everybody who is interested in this sort of things. But it's still an open question, I would say. Just the take-home message is that it's still an open question, that these considerations should be taken into account. Thanks for your attention at the end. And this is my email if you are very interested to just contact me, or we can have more discussion about it. Thank you, Ajay.
Thanks, Meisam. Really nice talk. I think we can open the forum for any questions. Okay, so when people are thinking about it, maybe I can ask a few of them.
Yeah.
So, I mean, you are showing some of these contact-related constraints, right?
Yeah.
So, if it's the growth in like a soft material, then that would lead to some kind of instabilities.
Yeah.
Like buckling, right? So, how did you account for those?
Yeah, very good question. Maybe I can just go back to, I mean, here the buckling basically didn't happen because this growing material is embedded in a soft, itself, it's a soft material, but it is also embedded in a soft material. So it's, you know, of course, from mathematical point of view, in this case also we might have this formation of this wrinkling, as I explained. but we didn't experience this buckling here. But in this case, we had some sort of this buckling problem. So in the, you know that in the buckling problem, what happens is that you are facing this bifurcation in the solution procedure. So you need to enhance your solution procedure in order to sort of keep the problem stable. In particular, for this problem, it was very horrible because the material come into contact several times, and then you see that it's very, very difficult to get this convergence. Even here we have a self-contact. So if we are talking about constrained growth that intrinsically lead to compressive stresses, so to say, so they are susceptible to this type of instability or buckling that are to be treated carefully. So, for example, in ANSYS, I had to activate in some cases line search, in some cases arc length, with the particular care.
Okay, I see. And okay, I was thinking of something else. I forgot about that. But then if there's somebody else with a question, then I think we should open it up for.
Yeah, and the second thing I can also I just recall it because I did it like 1 year ago. The second thing that I recall is that in this model you have a parameters that is called sigma critical, and that sigma critical is the sigma at which the growth stops, right?
Okay.
So this is a very good thing, that if you use this sigma critical larger than this buckling sigma, I would say, roughly speaking, this is problematic because it means that you face buckling before your growth stops. But if the sigma is defined sufficiently smaller compared to that critical stress that is associated with the buckling, in this case, you don't basically face buckling because before that the growth has stopped in that direction. So you expect, yes. So this is also something that I remember that in some cases where we had this problems. So what we did is that, because it's a mathematical model right now, I mean, you can ask what's the physical meaning of that sigma critical? I have no answer to that. It's only mathematical model that if that should be sort of investigated using the in vitro and in vivo studies. So these material parameters, first of all, should be meaningful, should be measurable. And then, but what we did is that just to use the good parameters, just to avoid that problem. But in some cases, for example, I remember that for this case, because the contact is very, very often, and then there's no way to just decrease that sort of sigma critical. I remember that if I recall correctly, the ratio of the volume change is around 40. That means that the volume increases 40 times. And this little sphere is to just fill the available space in this very, very complex geometry. And a lot of stress is sort of trapped there. A lot of stress is accumulated there, and there's no way. And I remember that we had some surface instabilities, some surface buckling due to those things.
Yeah, that's really interesting, I think, to look at these instabilities and how to go about them.
Yeah.
But then, like, okay, now since you raised the question of parameters, like, how do you get these numbers, right? I mean, that's another question that's always haunts me when I look at biomechanics paper. Where do you get these numbers from, right?
I mean, since this model is basically a model that's proposed by us, by me in principle, so right now they are only numbers. It's a very simple answer that I can tell you. Right now they are only numbers. That means that I can show to you the model parameters. In particular, if I can find it. They are right now only numbers. Here. This sigma critical, that is it's like something like yield stress. I mean, for the structural mechanics, it's measurable. That means that you do this dog bone tensile test, and then you just simply measure this yield stress, right? But here, the measurement of this guy is not easy. I mean, because it's a stress at which the growth stops, right? Stress at which the growth stops. So for me right now, it's a number. It's only a number just to check the mathematical model. And then what else do we have? We have some parameters related to this coupling between this one, K1 and K2, that are related to this coupling between the concentration and the mechanics or the growth. I mean, these free energy, you can assume that, okay, they are like the Young modulus and the Poisson ratio of these biological tissues that are measurable and available in the literature for any soft tissues that you have. I mean, so these things we use like...
That seems something like a neo-Hookean kind of a model.
Exactly. So exactly, they are Lamé parameters. Exactly. And then for the soft tissues, we use in the literature available values. But for the parameters that were introduced due to this framework, to this model, of course, we only use some I would say rationally justifiable numbers. That's it.
Okay.
Yeah, but of course you are right. I mean, this work should be enhanced. It should be improved by just coupling this in silico experiments, I would say, with the in vitro and in vivo real experiments. And in that case, one can measure, one can look at the sensitivity, and one can really define those parameters. But right now, it's purely mathematical and numerical.
Right. No, I completely agree. I think the measuring these numbers are a different ball game itself. I don't think it's easy to just. I mean, nobody is going to give you the brain to just like put your hand into it and like, let me make a measurement. Right. So, right. So it's a different thing. I totally agree on that one. And then I mean, since we are talking about these soft materials, aren't they viscoelastic, or do you think that would make any difference in there?
Yeah, absolutely. You are right, Ajay. I mean, right now, the viscous effect are completely excluded from the model. But one of my direction for the extension of this work is exactly viscoelasticity. I mean, maybe we start with this linear viscoelastic framework that is easier. That is this Prony series, better than me because it's the field of your expertise. And then after that, and then of course we need to introduce a new relaxation time in order to characterize that viscous effect. But you are completely right. I mean, for the soft tissues, biological tissues, I would say, if you ask me that what is the most important player, I would say viscosity. For sure, because all of these biological cells, I mean, if you look at the microstructure, you have a matrix and then you have this interstitial fluid. So we are talking about like a porous media, and then intrinsically you always have a dissipation of the energy at that scale, and they should be taken into account. But unfortunately, right now it's completely excluded from the model. So this model, the already existing model, is only elastic plus this growth. Elastic plus this growth, but you are completely right. I mean, it's a very important thing that should be, not could be, should be taken into account for this.
Because probably that would also play a critical role in delaying your instability somehow, if I'm correct.
Yes.
Right. If not, I mean, I'm just guessing. I have no idea, but I'm just guessing here. Right. And so, okay. So I think if somebody else has a question, please unmute yourself and.
Such a nice discussion. Question.
I think somebody
is talking, but I can barely hear.
I'm not able to hear either.
Can you hear me?
Vinayak, could you speak up a little loudly?
Yes.
Yeah. Can you hear me now, sir?
Yes, but not yes. That would be great if you just, I don't know, just get closer to the mic, or
Professor, can you hear me now?
Yeah,
Now
it's
it's,
better.
now it's perfect.
So, we have assumed here that the growth stops at a certain critical stress value, right?
Yes.
So I understand that suppose the material is growing isotropically and it encounters a resistance in a particular direction, so it will stop there at the critical stress value in that direction, and then it will start growing in some other direction, in the
Yes.
perpendicular. But suppose all the directions are exhausted and it completely fills the outside envelope. Then how does the growth stop? I mean, biologically still the cells are being divided.
No, this is exactly the point. I mean, this is a very good question. I mean, if you look at this case, this is exactly the case that you're referring to. The first contact, second contact, and the third contact. As I told you, it's a quarter of the model. So basically, now the whole space has been taken by this growing cube, I would say. You see that after that, everything remains constant. You get a plateau in all stresses and 3 levels of stresses, because the first one, this one, and then you have some addition of the stress due to Poisson effect, and then the second one and the third one. And after that, you see that all the stresses remain constant. But the point is that once all the contacts are established, just place yourself let's place ourselves in the shoes of those growing cells. So they just grow, they just from a mathematical point of view, as soon as you take the whole space, since you have no increase in the volume, you cannot have the increase in the volume, so your stress increase rapidly. And then once you reach that criteria, that sigma critical in the 3 direction, keep in mind that it's a tensorial representation of that. Look, it's a tensorial representation. It means that the growth might stop here, but still we have growth in these 2 directions. And then once all of them, they reach this criteria, then you have the 0 growth. That means that your L becomes 0 tensor. That means that you have no further growth. That means that your Fg remains constant, right? Because Fc is nothing else than the time integration of this guy, right? This velocity gradient is integrated using this exponential mapping, as I explained to you, and then you build your Fg. When Fg is constant, then your Fe is constant. So the whole system is frozen and you have no growth. Then I would like to come back to the question of Ajay. I mean, if we had some viscous mechanism, for example, in this case, we might have a drop in the stress due to viscous effect, something similar to relaxation, right? Something similar to relaxation, in which you apply a stress, but the stress basically drops over the time. Right now, it's not embedded in the model. So right now, we have the growth. We have the growth in all directions if everything is free. Then after that, upon appearance of the contact, some of directions are excluded from this L. And then once all of them, they reach that threshold, then L becomes 0 tensor. And then everything is frozen. So the growth is automatically stopped due to this feedback, because in the definition of the growth, we have not only that alpha, that is a function of concentration, but also it's a function of sigma. So keep in mind that in this model of the growth, we have two, I would say, 2 variables that the growth is a function of. The first one is the concentration, that you can assume that it's the driver of the force. The second one is the stress, that is the controller of the growth. It controls that how the growth is to be and where the growth is to be directed, and second, when the growth is to be stopped. Is it clear?
Yes. So the remodeling can still happen, right?
Sorry?
The remodeling at any point after the after the envelope is covered, completely filled.
Yeah.
The nutrients are still being supplied to the material, so cells
Yes.
are still being divided, and
although macroscopically we won't see any growth, but at each point still the remodeling of the system is happening. The density is increasing and all those things.
Very good question. It's not right now. It's not embedded. I mean, what you are saying, it's an hypothesis. It means that we can add something on top of it, saying that, okay, if the growth tensor becomes 0, then let's increase density. Right now, the density doesn't change. Keep in mind. Right now, the density doesn't change. It means that whatever new material is created is converted into volume increase, that we call it growth. But what you are saying, it's a good hypothesis that can be extended. So it means that at a certain point we have growth. If we have available space, we have growth. But if we have a limitation in that, then we activate this remodeling process. Right now, it's not there. Right now, what happens is that if the whole space is taken, everything just becomes frozen. Stops. So that means that the cells, they just consume the nutrient to the extent that they remain alive. That's it. So they don't give birth. They don't make this binary division or this fission in order to replicate themselves, in order to reproduce the new cells. So this is what happens. There is another possibilities. You can say that if the cells are confined, right now this shrinkage parameter is 0 in the modeling. The other model is that if they are sort of trapped for a while, then we should start activating the decay mechanisms. That means that that cube should start to shrink, right? So you have something that grows, and then once it's completely confined by the walls, then after that you can activate the shrinkage. This is also a possibility. This is also something, a direction that you can think. But right now we have assumed that K2 is 0, so we have no shrinkage. But if we had a shrinkage, we might reach a state at which this shrinking process is initiated. Because the shrinkage and growth from a mathematical point of view, they are really the same thing. This is only the opposite, I would say the opposite of that one. So it's only about a minus. If this the divergence of this L, if it's negative instead of positive, then this one. If it's the divergence is negative instead of positive, then you get this shrinkage instead of growth.
Understood. Thank you, Professor.
Yeah, no problem.
I have a question. So, hello?
Yes, go ahead, please.
Yeah, you have shown that ingrowth models, right? Can you go to that side once? So,
which one?
Ingrowth models.
Yeah, ingrowth in the bone.
Yes.
Yes, just give me, yes, this one.
So yeah, if I have a like that upper surface, say like at the outer surface, they are downside, and at the middle surface there is a big cavity inside.
Yes.
So if the bone starts growing and then like it starts penetrated first on the outer side, so there will be a trapped air inside it.
Yeah.
So
yeah, very good question. I mean, these are very I would say deep down questions. I mean, right now we have assumed that everything is in the space, in the empty space. So it means that there is no resistance due to this initial fluid that has occupied that void. You could have also raised the same question here. I mean, this. Yeah. I mean, I explained it quickly here. I told to you that okay, we say that it's a cube, it's a confined cube. it's growing. So if it's filled with some fluid, then what happens to that fluid? Because the accumulation of the pressure in that fluid also is like a barrier. So these, for example, these surfaces, they are not free. Then I told you that we have assumed that if there's a fluid here, these walls are permeable. So you can assume that they are perforated. You have some holes, very fine holes in it. And then the fluid can freely just escape. So this is the assumption that we have in what we are talking. But what you, Ray, mentioned is absolutely correct. So this problem, this is why that, I mean, there's a lot of things can be incorporated into this model. Just imagine that in this model, we want to solve this problem in the presence of fluid, a real fluid. I mean, right now we don't have fluid, right? Right now we don't have fluid in the empty space. But assume that we really want to solve this problem in the presence of fluid, and that's doable. Because as I told you, this is the good thing about working with this FEM solver, standard solver. I mean, you need to develop your own user element. I mean, at the beginning, it's not an easy thing. It's an advanced, I would say, usage of these packages. But the good thing is that if you want to incorporate the fluid into the problem, you know that ANSYS has a very good solver, Fluent and CFX. So then what you need to do is just to bring this Fluent or the fluid solver into the system, and then look how this interaction between this growing body and the fluid works. That's it. That's it, the good thing. So this also can be a good direction for the extension of this work. And I do agree with you. And we were also thinking about it. So we have different possibilities. One was truly mentioned by Ajay. The viscous effect is absent. The viscous effect is absent. The second thing, the incorporation of the surrounding fluid explicitly. That means that how that fluid, in particular, if you develop some pressure within the fluid, then that pressure also will influence the pattern of the growth of this body, because
yes,
it exists everywhere, and then it sort of confine, not like a rigid body, it's something else. Of course, you have some flexibilities, of course, but nevertheless, it can also affect it. This is also a second direction for the extension that we have also thought about it. But any new ideas about the extension of this work is welcome, and I'm eager to hear it. So these two are the two things that we already thought about it, and they are very good. Thank you for your question.
Yeah, nice way of presentation.
Yeah.
Good one. There are lots of insights.
Yeah, thank you. Thank you.
Hello, doctor.
Hello?
Sorry, I have a question.
Yeah, go ahead, please.
I'm sorry, I might be a little unclear about how the bulking doesn't start after the tumor totally confined by the spaces. If I'm wrong, please.
Could you please just elaborate more on your question? I didn't get.
I mean, when the tumor starts to grow
Yes.
and after it's totally confined by the spaces, the quarter element you showed in the presentation. After it's totally confined, you said it starts to shrinkage. But if I'm right, you said it doesn't start to bulking. And how does that happen?
You are talking about a tumor case, this one. This one, right?
Yes, of course.
Okay. It's about the brain tumor. I mean, what I said is that, I mean, what's the difference of this problem compared to the problem that I already discussed, that growing sphere and in this cube? The difference is that here, the surrounding barriers, it's elastic, so it's not rigid. So that means that upon growing this guy, you start to develop some compressive loads within itself. Instead, you create some tensile stress in the brain, in the surrounding healthy tumor. This is very important. So it's like this. So the tumor grows, the tumor grows, and then this part of the brain, the healthy tissue, is also stressed. So it develops some tensile stress. It's like you can assume that it's like a pressure vessel that you sort of pressurize it from inside, and what you get is that you get some tensile stresses, some tensile tangential stresses. This is only an example just to make you understand the mechanisms, what's happening there. What I said is that I mean, here is exactly related to the previous question that one of the audience basically raised. Here, the surrounding tissue, this elastic surrounding tissue, is pretty similar to the fluid, to the surrounding fluid. You see that this growth leads to the accumulation of the stress in the surrounding tissues, and this stress is something that confines the growth of this. That means that if we have the tensile in the surrounding healthy tissues, you have the compressive stresses within the tumor itself, okay? And then if this compressive stresses exceeds that sigma critical, that was a threshold, then the growth stops. Then the growth stops. And then in this case, what I said is that this can be one interpretation of emergence of some dormant tumor. Dormant tumor is something that has reached a size and then it remains constant. So this is one interpretation of that. There are a lot of interpretation for that. For example, the second interpretation is that if you have a dormant tumor, it means that the rate of reproduction and the rate of hypoxis, that means that the death of the cell is the same, so they are in equilibrium. So the number of the cells that are created equals the number of the cells that are dying. So this is like another interpretation of this dormant tumor. The outcome of this theory that I presented here is that if the extent of compressive load within the tumor reaches that threshold, in that case, the tumor cannot grow further, because if it grows, then that threshold is violated. So it's like, so that the tumor reaches that maximum allowable, I would say, pressure under which it can grow, right? This is basically the meaning. Then I told you that if you activate for whatever reason some decay mechanisms, then you might get a shrinkage, like this getting smaller and smaller of the tumor. Keep in mind that here, please keep in mind that here we are not talking about the real biology, because I am an engineer. So what I'm just presenting is the mathematical model and numerical implementation and the predictions. This is the most important part. The predictions that this model can make, and then try to justify or try to explain what is the outcome of this model.
Thank you, doctor. I didn't consume that the barrier of the tumor, which is brain, is elastic. So I'm totally understood now.
Yeah, it's elastic. I mean, it's basically a growing body embedded in an elastic body. So it's like the very concise description of the problem. The difference of this problem compared to these two problems, here we have the growing body against a rigid thing. Here we are talking about a growing body against an elastic thing, but both they are solids. And then the third possibility, as one of the students, one of the audience raised, could be the growing of a body against rigid or elastic obstacles or media, and then in the presence of some fluid. This is also a new thing that could be brought into the picture.
Thank you very much.
Yeah.
We have taken a lot of time from Meisam. Are there any further questions? But If there are not any, then I have one last question. Probably, Meisam, since all these biological problems are extremely stochastic in nature, maybe bringing in some UQ or uncertainty quantification could really make these more revolutionary, right? Or more useful directly, right? I mean, because I mean, some of these numbers, let's say the material parameters that we choose itself could be have a huge variance and mean. And depending on what they are, that could be lead to completely different things that we never thought about, I would say, right?
Yeah, absolutely. Absolutely. This is also, I would call it a third direction for the extension of this work, really.
Right.
Because, you know, I mean, unlike the structural materials, I mean, the biological materials, they are really, the values are really scattered. And so even, for example, if you look at the young modulus of the brain, right? It differs even for men and women, young and old people, and then different things, different textures. So here we always talking about an interval of the values. And then the sensitivity of the model of those, the certainty of the value is very important. And in particular, if you want to extend this work and sort of improve it by the clinical observation and experiment, in this case, then one should be able to just predict the things based on a patient-specific values. And then exactly this stochasticity is very important and should be taken into account. And so I would say that this is like a third dimension for the extension of this work, that in this case, I think this direction can be really boosted by the in vivo and vitro experiments. So it really gives like meaningful things one can really measure to look at the scatteredness of the parameters and the numbers that are present in the model, and then look how these things can affect the predictions.
I see.
Yeah.
It sounds interesting.
Yeah, absolutely.
So are there any further questions? If there are no other questions, then I think we could close this session. I mean, you all have the contact of Meisam, and I'm sure he would welcome any questions and would be very happy to discuss them with you. I would firstly thank all the participants for joining in, and also I would thank Meisam for the really engaging lecture. And I mean, it was really detailed, and I mean, I got a couple of feedback already that people really liked it, and they were able to understand the entire lecture, like step by step of things, of how things are being done, what's happening in there, and the nitty gritty of things, which is sometimes missing in most of the many lectures, I would say, right? I mean, it was really nice, and I learned a lot about how to model these biological materials and what is being done. And there's a lot of open questions, like you said, and that we could always look into and answer. And thank you so much for joining in on a Saturday and engaging the audience. I hope you also enjoyed it, and I would look forward to everyone joining in for the next lecture. Thank you so much. Thank you, Meisam. Thank you all the participants for joining in, and have a great weekend.
Yeah. Thank you very much, Ajay, for organizing this this program, this session. I am really thankful to all the audiences. Very good questions were raised. I liked it, and also you. I'm so grateful to them, and thank you very much. It was basically unique opportunities and pleasure for me to be with you and share my research with you. Please do not hesitate to contact me if you have any question, or if you have new ideas, something to be discussed. So with this, I would also wish all of you a pleasant weekend, of course, for those who are in Europe, in the US. And thank you again, Ajay. We will be in touch. Thank you very much.